Good morning. Here we are again. It's the new year. We have one more big topic to talk about before we wrap up this semester. And that topic is momentum. I'm sure you've heard of momentum before, and it's a pretty straightforward concept. I don't think you guys will have too much trouble understanding. In this video, I'm going to go through some of the general concepts of momentum. And my examples are going to be found more in the bell ringers of our meetings. So I'll just kind of go through the main equations that you'll need to know and talk about what momentum is. So first of all, momentum is this quantity, it's a vector quantity that an object can have. And you've probably heard about how a football team might have the momentum. Well, there's a sort of an everyday usage of the word, and then there's a physics perspective, and they relate to each other, but they're definitely a bit different. In physics, momentum is strictly just the mass of an object multiplied by its velocity. So those are two quantities that we've used a fair bit in this class. And the velocity has a direction associated with it, and so the direction of the momentum vector is going to be in the same direction as that velocity vector. And I bet you can figure out what the units of momentum are going to be here. Our mass is measured in kilograms and our velocity is meters per second. So our units are going to be kilograms multiplied by meters per second. There isn't a special unit that equals a kilogram times a meter per second. We just sort of write that out. So one of the big uses of momentum and why we need to learn about it is it's useful to understand collisions, and it's useful to understand explosions, and it's useful to understand recoil. And so if we think about a couple of football players colliding on the field, both of those players have mass, and they both have velocity in different directions. And we might want to know after a collision what the direction of the two football players together might be, their direction and that velocity, and so the final momentum after the collision. And so we can predict this if we know the initial momentum of each individual football player. One of the topics that we'll need to discuss first before we get to collision problems is something called the impulse, which is the same thing as this change in momentum. So if you look at the second equation here, I have the net force equal to change in momentum divided by change in time. And the impulse is going to be this quantity that changes the momentum of the system. I can rearrange this equation and move the delta t value over to the left-hand side here to get a quantity which can change the momentum of the system. And so if I want to increase an object's momentum, I'm going to have to apply a net force to that object, which should fall in line with our understandings about acceleration and net force and Newton's second law. So here we have the equation I was talking about, the rearrangement of the equation from the previous slide, where I've multiplied delta t over to the net force to get a quantity known as impulse. And so here we have it, the impulse is the average net force multiplied by the time interval of contact. So what we have here is really a collision. What we're saying is how long this tennis racket is in contact with the tennis ball multiplied by the force exerted is going to change the momentum of this tennis ball. It's going to go from either a velocity in one direction back to the other side of the court, or from no velocity to some velocity. And so the objects here, as we have this collision, the tennis ball and the racket, are going to be deformed during this collision due to the large forces involved. Now, one of the big understandings with momentum and collisions is how the time interval affects the average force required during a collision. If we increase the time interval, what that does is it allows for a smaller force value to act to achieve the same impulse. Or on the other hand, if we decrease the time interval, what that does is it makes a really big average net force to create the same impulse. So basically what I'm saying here is a small time interval is going to give you a big force, and a large time interval is going to give you a really small force. So we can sort of decrease the magnitude of the force if we can create a longer collision time. And this should make sense if we think about something like a car. And the car has, during a collision, a crumple zone that allows for a larger time interval for that collision to take place over. Even if the time interval isn't dramatically different, even if we change it on the order of milliseconds, we can reduce the forces on the passengers during the collision. Or the same sort of thing with the airbag. If we can make that collision between your head and the airbag last longer, that's going to decrease the average net force. If that collision happens over a smaller time interval, if we didn't have the airbag to sort of extend the collision, the force would be a lot bigger. So the larger force is obviously more dangerous, and so airbags have saved a lot of lives based on this physical principle. So let's think about this guy who's jumping up into the air and then landing. So as he's falling back towards the ground with a velocity of 7.7 meters per second, he's going to have an impact. He's going to have a collision between his body and the ground. And how he lands is going to make a big difference on the amount of force that his body experiences. In both cases, his change in momentum is going to be the same. He's going to have some initial momentum, his mass multiplied by his velocity in the downward direction. However, how we absorb that momentum change is going to have a big impact on the force. So where the impulse is going to remain the same, the force and the time interval are variables that we can sort of adjust based on how we do this. So in the picture here, the guy is bending his knees, and so what that does is that is going to increase the time interval during the collision, and then that's going to decrease the force acting on the person, so he's not going to hurt himself. If you tried to land with your legs straight and you didn't bend your legs at all, that time interval would get much smaller, and then that would make the force much larger. So these two things are sort of opposites. One has to go up, the other has to go down, because the impulse or the change in momentum is going to be the same thing no matter what we do, but we can increase that time interval to decrease the force. And so this explains a lot of physical situations on how we reduce forces during collisions. One of the most powerful applications of momentum, especially for collisions, is this idea that momentum is conserved. And what that means is the initial momentum of the objects before a collision is going to be the same as the final momentum of the objects after the collision, as long as we keep an isolated closed system. And what that means is that we have no external forces acting, and that we also have no additional mass being added to the system. And so what we have here is a train car coming in from the left with a velocity of 24 meters per second. It's going to collide with a train car at rest. And both of these train cars, we're going to say, are in this system. And so what we expect is my total initial momentum is going to be the same as my final momentum of this system. And so if I wanted to find the initial momentum of this system, what I would do is I would take the mass of car A and multiply it by its velocity. And then I would take the mass of car B and multiply it by its velocity. But you can see that since car B has no velocity there, its momentum is going to be 0. But we still want to take that into account. So after the collision, both of the cars are now moving together. They've sort of coupled it together. We would need to add both of their masses and multiply by a shared mutual velocity to find that um, final momentum of the system. But so this is a really powerful concept which we'll be exploring in our lab this week. And so in an equation form, what we have here is the mass of velocity of object A multiplied by the velocity of object A plus the mass of object B times the velocity of object B. That is going to be the total initial momentum of the system. So everything on the left-hand side of this equation represents the total momentum before the collision. And after the collision, we're going to expect the same exact thing. We're going to expect to have the final momentum equal the initial momentum, although we might break it up and look at, well, what's happening with ball B and what's happening with ball A. So what if the masses of ball A and B were totally identical and their velocities were equal yet opposite in this picture right here? What would the total momentum of this system be initially? Well, let's say this was a mass of 1 kilogram and that had a velocity of 1 meter per second. Its momentum would be 1 kilogram meter per second to the right. And this one would have a momentum of negative 1 kilogram meter per second. And so the total momentum of this system before the collision would be 0. And so we would expect that after the collision, the momentum of both of these balls combined would also be 0. And so what would happen is we could predict, well, their masses aren't going to change, and their velocities would have to be exactly the same thing, 1 meter per second, but in opposite directions. So one of the things we'll be modeling in the lab this week are a couple different types of collisions. You might have heard of elastic collisions and inelastic collisions before. So let's talk about that briefly here. An elastic collision is kind of what you imagine, like two bouncy balls hit each other and they bounce apart in opposite directions. They're rubbery. There's no crumpling or deformation, and the kinetic energy, which is a quantity we haven't learned about yet, is going to be conserved. So for now, since we haven't talked about kinetic energy, the difference between elastic and inelastic, at least perfectly inelastic, inelastic would be where the two objects sort of stick together, like the train example that I just talked about. So if two objects come together, collide, and sort of stick together, we're going to call that completely inelastic. And if the objects bounce apart, we're going to call that elastic for now. But technically, for a perfectly elastic collision, the total kinetic energy of the system is also going to be conserved. And that's going to be our next unit after I guess at the start of next semester will be the energy unit. And we'll definitely delve deeply into what kinetic energy is and all of that good stuff. So I think that's about it for now. Yeah, hopefully that all made sense. And if not, please hit me up for questions. All right, have a good one.